Vancouver.
So we get to hang out with you guys for about 2 hours and a very fun lineup of speakers. We're going to move quickly because there are a number of them, but we have some built-in time for some discussion or if things run over a little bit. So Mauro Oddo, let's take it away. You're first. Thank you.
Thank you. Thank you. Good afternoon, everyone. Indeed, we have to rush through several talks and speakers. So I was assigned to the topic of building efficient data-driven research. And these sessions is about principles. I have no disclosures in relationship with this presentation. So I'm going to give you some principles on how to build efficient data-driven clinical research. And I tried and summarized based on a review that you can read, which was published 2 years ago, on a sort of flow on how to collect data. And one important point is definitely to have a data collection of sufficiently high quality. And this is one very challenging thing when starting building up data-driven research. So collect data that are within the electronic health records that can then be available, clean and processed to then provide an integration of this data from different sources and build up a data set which you can then explore with available statistical analysis. So first of all, in terms of exploratory analysis, look at trends, patterns, and relationships between these data, and then try and build up predictive models with the use of advanced statistics, basically regression analysis, several techniques, and we're going to discuss, I think, quite a lot over this afternoon about machine learning. And definitely the importance of having a bioinformatic group of people within your center that are able to make out relevant things about those data. There are several other things that can be exploited with the use of data-driven clinical research. And it may be also useful to think about in terms of following up patients longitudinally through digital platforms and also to engage patients more easily in these follow-up. It's also something that can optimize trial design and more often also in other fields of medicine like neurology or cardiology, we see that the monitoring of patients at distance remotely can be made through digital tools. And finally, what we aim with the use of data-driven clinical research is to have therapies that are targeted, so-called precision or personalized medicine. And we have seen this morning, and I will give you a few examples on how this can be used. We have seen this morning the oxygen targets that can be basically targeted and can vary in terms of mortality depending which type of patient you are. And we saw a 6.4 percentage difference in the absolute mortality. So this can make changes, and it's very gives a lot of sense in terms of data-driven clinical research. I think there are few key factors to take into consideration when we think about the digitalization of healthcare data. There are many standards available also in terms of regulatory, legal, security. So to build up digitalization and this conversion is very important. Also advances in data science and analytics, specifically new statistical and machine learning methods, And I will finish my talk by giving you an example of data sharing initiative that was started in 2018 in Switzerland to connect the several university hospitals, and now moving to even larger hospital, not only university, but also in the cantons within Switzerland. So I think that these increasing effort to open data and to have a large data sharing data set is also something very important. Now, data-driven research in the ICU, this is a summary of what we're going to discuss and the different terminology between artificial intelligence, data science, which is understanding data, and then using statistical tools to learn from this data. These are specifically machine learning. And I just would like to spend a little bit more of time on this aspect of machine learning. You see the different types of possibilities. On the left hand side, you have the so-called supervised learning, which is mostly focused on prediction, and so identify using a different set of variables that can predict treatment response or predict individuals that may be of benefit from an intervention versus those who may be actually harmed. So if you take the example of a septic patient, you can train the model to distinguish patients with sepsis versus without, and then use this model, which is trained, applied to a different set of data using statistical tools, essentially logistic regression. And then you have a sepsis prediction model that then you can apply to a different data set and test. Versus the unsupervised learning, which allows you to identify different subgroups or subphenotypes of individuals that you wish to include in a type of therapy, and to distinguish between those who may benefit versus harm. And for this, you use other types of algorithm of statistics, like the k-means clustering or latent class analysis, which will be discussed later on. And then you have phenotypes of pathologies, which are syndromes like sepsis, ARDS, that you can distinguish within these large syndromes subphenotypes. I wish to give you just a few examples from our center in Lausanne, where we have established now 3 years ago a biomedical data science center. So it's a group of bioinformaticians that basically offer services throughout the hospital at different level, different services. And here are 3 examples, just to also give you the impact, the potential impact of data-driven research, not only in terms of treating patients, but also in other aspects of healthcare. And you see on the left panel, I put administration, because using an AI model, we were able actually, the group of Jean-Louis Rézaro within the CHUV in Lausanne, to identify patients with complex coding, so basically several polymorbid patients, and they were able to successfully identify these codes. And obviously for the administration of the hospital, these may be very promising, because you can actually gain quite a lot in terms of finances if you code correctly these patients. In the center, a nursing study, which is also ongoing, to prevent long-term hospitalization in elderly patients. So with this model, which was deployed in the service of internal medicine, they were able to show that you can identify early on, within the first 48 hours, patients who may require longer hospitalization versus short hospitalization, so identify very early on at day 3 those patients who could get out from the hospital sooner and therefore shorten the length of stay in the hospital. And then in the end, a sepsis predictive model, which I'm going to spend 2 more slides, just to identify as well the fact that with the use of the septic predictive model, they were able to show that it's actually also very useful in terms of identifying the exact coding and therefore, again, financial gain. So this was a retrospective analysis conducted in 14 services within our hospital. They used machine learning approach to identify missed past cases over a 4-year duration. And this is a sort of pipeline and pre-processing. Quite a lot of variables used here, more than 20 set of variables, again across 14 services in the intermediate care unit. And what was very interesting in introducing this model, you see on the left panel that there was a number of patients which were administered antibiotics beyond 3 hours was reduced, and there was an impact as well on the length of hospital stay. So those in which this predictive model was used, the duration of hospital stay was reduced from 22 days down to 16 days. And again, you see on the bottom part of the slide a number of patients with delayed antibiotic administration was also significantly reduced. So these are still unpublished data, but showing you the value of using machine learning. Obviously, these models need to be now tested in a prospective way because this is still retrospective analysis, although available to physicians within 24, maximum 48 hours. Additional examples of the use of machine learning from one of the moderators, Christopher Seymour, these study on sepsis subphenotypes using unsupervised learning to identify 4 types of phenotypes, which then responded differently to volume resuscitation, and more recently the ARDS subphenotypes. What is very interesting in this study is that they used a first set of variable which complete a set of variables, more than 25 variables, and they were able to confirm that the secondary model with less variables, up to 4 variables, actually performed similarly to the primary model with 25 variables. Now, again, these needs to be tested more prospectively, as we have seen this morning with the oxygen targets. I will end my presentation by stressing really the importance not only of building infrastructure, but also building bridges across centers, and this is the Swiss Personalized Health Network, which started in 2017. Lausanne is part of it, and also was very instrumental in building up our data science center, and we are now in process of having results from several studies undergoing across these 5 centers in sepsis and also other diseases. With that, I thank you for your attention.
We don't quite have time for questions right now, but hopefully once discussion after the first 3 speakers, we'll be able to ask some questions for the speakers. So just moving on to the next speaker. This is Dr. Leo Celi from MIT, who's going to be talking about challenges in data collection in the ICU.
Thank you so much. It's great to be here. The title of the talk is Challenges in Data Collection in the ICU, but we don't really have any challenges because we collect so much data in the ICU. Before I rename the title of this talk, I just wanted to disclose that Our group receives research funding from the government as well as several industry partners. I thought the more apt title of this talk is Challenges in Using Data Collected in the ICU for Any Type of Study, not just machine learning, but also for clinical research. And I have divided them into 3 categories. The first is challenges in accessing the data so that you could perform research. And generally, there are 2 types of access. One access is that the data is only open to internal investigators, those who work in the hospital, and their collaborators. And that is by far the more common model that we see. The other one is open access. And we think that this is really a game changer, and it weakens power structures, because what we found in our study is that if the data is only accessible to internal investigators, you preserve the power structures. There are more white male professors that are publishing off that data compared to underrepresented investigators. And I was just showing the product of Mimic, which is a data set that's coming from our group. And since its publication, since its release, it has produced actually close to 10,000 papers now in Google Scholar. Some would argue, well, how many of those are garbage? But it's still beyond the point. We really think that this open data movement is a game changer. I'm aware of about 5 publicly available ICU data sets out there, from Mimic, which comes from the United States, the EICU Collaborative Research Database, which also comes from our group and would have data from more than 200 hospitals in the country. There's Amsterdam UMC DB from the Netherlands. There's also HIRID from Switzerland. And then the more recent one is a database coming from Austria. And I mentioned earlier that there is a smoldering open data science movement. In the United States now, if you want to get money from the government, you have to detail how you're going to de-identify your data and share it with the rest of the research community. So there is really a push for data sharing. And then also starting at the end of the year, they're also going to mandate that journals will no longer be able to embargo any paper where one of the investigators is funded through the government, that these papers will be released at the time of publication. The next group of challenges in using data collected in the ICU for any type of study is the challenge of curation. Curation is the bane of real-world data research. We spend 90% of our time curating the data. And what does curation mean? It means that you are referring to the same concept when you are analyzing data coming from the different ICUs. If you say blood pressure, what do you mean? Do you mean mean arterial pressure? Do you mean systolic blood pressure? Do you mean diastolic? Are you referring to blood pressure taken by an arterial line, or are you referring to a blood pressure taken by a cuff? So all of those need to be standardized before you could really perform research on ICU data. And here I actually named 4 categories of databases depending on how curation process is going to take place. We have commercial databases. There is data coming from Optum, and you could buy them for a lot of dollars. And they have been curated for you. The question is, who curated them, and can we trust their curation? Did the curation process introduce bias? So we wrote a paper that's very critical of these commercial databases. The next one, which is the ideal way of curation, is what we have for Mimic and EICU, where it's truly open, and we actually encourage, or if not, we cannot mandate it, but we have users of our data sets promise that they will share their curation, they will share their notebooks, their Jupyter notebooks, their GitHub repositories. And what this does is that there is a quality check. So people get to see how other groups were able to curate a certain concept. And they also contribute to making sure that the curation is accurate. And there's a mechanism by which you could say that, hey, your curation before is not really reliable, and here is a way of curating this particular concept, and they would submit that to us, and then we would share that with the research community. So we think that this is the way to go, especially as we're swimming now in ICU data. There's also what we call the open in appearance only. They say that they are publicly available, sometimes at a low cost, but everyone has to start from scratch because there's no mechanism by which different groups are able to share their curation. And of course, the last one, which is the worst, is when data is closed and it's only accessible to internal investigators and their collaborators, because there is no way. Sometimes they don't even share how they curated the database for that particular study. And then the last, which is the most complicated challenge in using data collected in the ICU, not just for machine learning, but for clinical research, would be all the data issues. And this is also known as social patterning of the data generation process. And most people who do machine learning are not really familiar with these types of problems. And here I enumerated 3 problems with the data, not just coming from the ICU, but coming from all hospitals and clinics. The first one is sampling selection bias from social determinants of health. Who made it to your ICU? Are some groups systematically excluded because they don't have access to the ICU? Or were they discriminated against, like they got admitted to the floor and then they died on the floor because they should have been admitted to the ICU? So this creates a sampling selection bias, which I will talk about very soon. And then there's also that large category of what we refer to as largely invisible social determinants of care. And then the last category is technology bias. So I'm going to very quickly give an example of a sampling selection bias from social determinants of health. And this study came out during the pandemic, and they were looking for predictors of death if someone gets admitted to the hospital with COVID. But they use the database coming from the Veterans Administration. These are people who served in the Army, the Air Force, as well as those who retired from serving in the military. And this is the main table of that study. If you look at the first third of the table, it makes sense. As the patient grows older, the risk of death goes higher. But if you look at the middle third of that table, it tells you that people who never smoked have a higher risk of death from COVID. And the last third of the table is also saying something very questionable, that people who are obese are more likely to survive after hospitalization from COVID. And if you're not careful and you're building a model, the model will learn this and will use this as its rules for predicting whether you're going to survive or die from COVID. So what happened here? It turns out that among veterans, smokers are much more common than non-smokers. And people who don't smoke, who get COVID, are not likely to be admitted to the hospital. They get excluded from your cohort. And the same is true with obesity. Veterans who are not obese, who develop COVID, are unlikely to be admitted to the hospital. So your cohort now is not representative of the target population that you're building an algorithm for. Then second to the last group of this data issues is the largely invisible social determinants of care. It turns out that the routine care, which we normally do not include in our models, is not uniformly administered. And I'll give you 2 examples. And then we also found problems with frequency of monitoring of vital signs, laboratory tests. They are not identical across different patient groups, and it's not explained by the disease or the phenotype of the disease. And the last example of this is the missing data problem, and the good example is the sex and race concordance between providers and patients, which we know affect outcomes, but you don't have that data in your data set. So this is a study that we are wrapping up. It's actually going to be presented in the poster, where we looked at the frequency of mouth care among patients who were intubated, and we also looked at the frequency of turning. Again, we assume that everyone is being turned, everyone's mouth is being cleaned every 4 hours, and we don't even include that in the modeling, but we found out that it's not uniform, that we were able to find a distribution when it comes to frequency of mouth care, a distribution when it comes to frequency of turning. And this could be the driver of why some patients actually had a worse outcome in the ICU. Unfortunately, we do not include this in our models. And here, we couldn't explain exactly who the patients are who got less turning and less proning. It's not race ethnicity. What we did find is that the heavier patients are turned less frequently. So it gave us confidence that this database is actually accurate, has fidelity. But what we found is that the people who were less turned were also the people who had less mouth care. And we're increasingly trying to come up with new labels. So rather than looking at white versus black, English proficient versus limited English proficiency, maybe we could come up with new labels referring to the quality and quantity of care that they received. And this one is looking at, are people getting serum lactate when they come in with sepsis in a consistent manner? And we actually found that there's also a difference in the likelihood that you're measuring different blood tests, from serum lactate to blood glucose. And again, what is the impact of this when you start building reinforcement learning models where this measurement is not uniformly obtained from patients? Of course, that's going to be problematic when you're trying to come up with the optimal policy. And the last category of this largely invisible social determinants of care is what I alluded to earlier, would be the race concordance or the sex concordance between the patient and providers. These are some studies that have shown that this is a strong driver of the eventual outcome. If we have heard about women patients having poorer outcomes when their surgeons are men as compared to when their surgeons are women. And we've also seen this with MIs, with heart attacks, that women have worse outcomes if the cardiologist is a man versus if a cardiologist is a woman. And what happens here is that the machines learn that it's actually being a woman that is a risk factor, because there are more male cardiologists, there are more male surgeons. So the machine starts learning all sorts of things if you don't have a complete data. And finally, the last category of data issues that you need to be aware of is technology bias. And the one that is most popular is the pulse oximeter. So that means that a certain number means different depending on the color of your skin. And this is a review paper that we published last year where we pointed out 8 devices in the ICU that don't perform similarly in an identical fashion across different populations, depending on the color of their skin, depending on their body habitus, depending on the type of hair that they have, because we have to stick EEG leads. So to summarize, these are the challenges in using data collected in the ICU for any type of study. There is challenges when it comes to access. There are challenges that relate to curation. And finally, the bigger, more complex challenges would pertain to data issues that not everyone may be familiar with. Thank you very much.
Thank you, Leo. A great highlight of the problem of bias in many of our data. Okay, so next we're going to move on without questions. We have a little bit of extra time from our discussion section that we will borrow, so Ari Ercole can join us from Cambridge for the next talk.
Thank you, ladies and gentlemen. Thanks to the organisers for the invitation to come and speak to you. So I'm going to talk a little bit about perhaps the slightly less kind of sexy end of things, which is how you get into data science. So I'm really aiming this at people who want to think about using routinely or otherwise collected data for interesting tasks pertaining to ICU or acute care. So there are a lot of opportunities from intensive care data. They've all been gone over. I'm sure I don't need to dwell on them. But you know, the thing that's really special about intensive care is that we measure an awful lot of stuff. Right, and it's quite hard to define our optimal care, but our patients are really well represented as a digital kind of avatar, right? They don't have voices very often, and therefore we measure an awful lot of things that hopefully represents them. So that gives us some opportunities to learn about biology, to learn about the treatments, and also our systems of care. And the last thing that's nice about routine data is that EHR data is, relatively speaking, cheap. The thing about ICU data that makes this tricky, though, is that it is big data. And by big data, I mean not only that it is large in terms of its volume, but it's also in terms of its variety, how quickly we get data and how quickly we need to make decisions from it, and also the amount of missingness and irregular data that data structures there are in intensive care. So this is not easy, and you need to do it right. And there is no single pathway into this. I've been doing data science one way or another for about 30 years, and I've got into it in a whole variety of different ways that are not really probably replicable. It doesn't matter. It's very, very accessible, but there isn't a single pathway into this. So what I'm really going to do in this talk is talk about how to do this properly, some basic principles that you probably want to just think about and adhere to in your way in. So the first one is don't get into trouble. Okay? in Europe, we are very lucky, and let's say this very often, but actually the laws that surround our data governance are actually really very permissive for research. And everyone will know about the GDPR. If you're working with de-identified data, and of course there is a question I don't have time to go into as to what de-identified really means, then of course GDPR doesn't even apply. That being said, there are differences across the member states in exactly how we can and cannot use even de-identified data. So just make sure that you're aware of what you're meant to be doing. Data is precious and we need to treat it with respect. If not, and these are some examples from particularly Cambridge Analytica from the UK, Cambridge Analytica and Royal Free Hospital, you can find yourself in a lot of trouble. Okay, so just need to respect data and regard it as a precious commodity that is potentially sensitive. The second, and I think really important thing for doctors and people in the medical profession is this, which is to free yourself from what I call the tyranny of the spreadsheet. Now, everybody in healthcare, and indeed in many industries, will be aware or think of data analysis as something you do in an Excel spreadsheet or in a spreadsheet. And that is not something that you can do with ICU data. Right? You have to abandon that paradigm of working with data. To give you an idea, this is a study that we did back in 2020. You look at the number of patients. We've got nearly 100,000 patients, 11,000 patients from a subset of data. I was, like everybody here, I think we were quite busy at that time as well, and yet we could pull this off relatively quickly. I'll tell you where you can get the data from if you want to look at the Brazilian database. You can go to this link, there's a QR code. Don't do it on your phone, because it will crash your phone, because what you will download is a 655 megabyte CSV file of over 1 million different episodes. Okay, if you try and open that in Excel, you won't get anywhere. But you also won't be able to do anything with the data either, because the format is, generally speaking, not the kind of format that you're interested in ICU. So in ICU, we have a lot of temporal data, and that doesn't represent itself well in a wide data format. You're all familiar with Excel of having, a patient, one row per patient, and then things are happening. In temporal data, that can't work. You can't have data point at time 1, time 2, time 3, time 4, because it'll be different lengths for every single patient, a very, very wide data set, and very, very difficult to handle. So data is fundamentally represented in different structures for ICU data, and to manipulate that, you need to do that programmatically. So the next bit about this, and to freeing yourself from this tyranny of the spreadsheet, is learning to think programmatically. Now, at this point in time particularly, that means learning how to do some sort of coding. So in fact, data science research, clinical research, medical research, is very, very akin to doing coding, to doing software development. You need to pick a language. I don't really care which one you use. The reality is, in practice, you're going to have to end up using multiple different languages. If you want a primer, if you do lots of statistical kind of stuff and want to draw graphs, which is a lot of biomedical research, R is very good. If you want to do slightly more kind of out there stuff, then Python. But it doesn't matter. In reality, you end up having to use both. You've got to learn to think programmatically, and I'll talk more about that in a moment. You may need to do other things. So really, really big data sets don't live in tables and CSV files, but they live in databases. So it may be, depending on where your data sits that you're interested, that you need to learn how to interact and deal with databases as well. Okay, which I won't go into here, but you just need to be flexible because the data won't come to you pre-curated typically. Now, I say learn to think programmatically, and at the moment that does mean learn to program. That may not be the case forever. Here I've asked ChatGPT to tell me how to program something. So there are tools that allow you to actually start synthesizing software, but caveat, someone needs to still just make sure that this is doing the thing that you think it's going to do. And increasingly we're seeing low-code and no-code techniques for data analysis, where you can essentially take different items and pass them through some sort of pipeline to get an output. That is still, however, thinking programmatically. Data, cleaning pipeline, analysis pipeline, visualization pipeline, or whatever. Right? It's all programmatic. That's not what you do with a spreadsheet, which is you take the data, you start manipulating, moving it around, doing things with it from the start. It doesn't work that way. Step 3, and this may not be super popular, but it's learn some statistics. Now, I think every single person, medical professional, needs to have at least some kind of basic level of statistical awareness. Otherwise, how can we have a chance of interpreting the basis of our evidence-based care? But I think if you really want to get stuck into data science, you probably want to elevate that a little bit to sort of at least an intermediate kind of level. The truth of the matter is that a really, really clever model will not fix garbage data. Okay? And the data that we get when it was collected, the person putting the data into your electronic health record was not thinking of your analysis. So there will be biases, variances in definition, there'll be errors, there'll be missingness, which might be informative, in fact. And the second thing is a wrong model will give you the wrong results, even if the data is right. So here I've got 4 different data sets that were published in the 70s by Anscombe, and they're constructed in a specific way. Now, if you look at it, the first one there's fitted a straight line to. The other ones, why would you fit a straight line? There's clearly an outlier in number 3. Why would you fit a straight line to a banana? And that's clearly the wrong model to fit. Okay, and then X4 obviously also is the wrong model to fit. This is data that only has 2 different, it's dichotomized X value. So this is the wrong model. Straight line model is the wrong model. But if you do it, you don't get arrested, the computer doesn't explode, no one will tell you there's a problem. And in fact, you will get exactly the same mean for all of these 4 things, exactly the same sample variance, exactly the same mean in the vertical axis, and the linear regression line is exactly the same. But it's meaningless because the model was wrong. So be very, very careful in understanding whether or not the model that you're actually fitting to data is right. Now, we all see linear regression in the literature. We're very, very familiar with it. I dare say most people in the audience have done linear regression on data. It's very easy to do, packages out there. But do you know that there are many laws that actually underpin whether or not those numbers that you get at the end mean anything or not, whether a p-value really means a p-value? And one of the ones that really messes us up in intensive care, particularly, laser's not working, if you look at the bottom, is no collinearity or uncorrelated error as well, is that we have time series data. And the best predictor of next blood pressure is not your age, your sex, your disease, your noradrenaline dose. No, the best predictor of next minute's blood pressure is this minute's blood pressure. They're correlated, and therefore linear regression breaks down. So you need to know some statistics, otherwise you will trip up at some point and make a mistake. Step 4 is be very systematic with your cleanliness, and Leo talked a little bit about this. Data quality, your results are only as good as the data and the model that you use, all right? So there has to be some sort of curation pipeline that either you apply or somebody applies, because if you don't have that curation pipeline, the answer you get, the decimal points or whatever, will depend on the curation decisions you make. Okay? So not only do you have to data curate, but you need to version control as well. So particularly if you're using data from your own institution, that data is not immutable. Okay? Someone may go back and change things, or there'll be new patients. So you need to be very clear, and that will change the answer that you get at the end. So for reproducible science, that's important. The data curation is seriously unsexy. Okay, this is what I think I do, because I'm a data scientist. This is what my friends think I do. The reality is this is really what I do. I spend an awful lot of time taking out the garbage and trying to fix data quality problems. As you're doing retrospective work, the data quality problems are there already. Here's some real data from a study across multiple different centres, some calcium values that have been from observational study. Can you guess what happened here? No one specified whether this should be ionized or total calcium. Okay, very hard without albumin and other things to actually disentangle this. And you just put this into a regression without looking at all these data quality issues, you will make false inferences. We've written some best practice guidelines to think about how you do curation. The best thing to do is to try and fix the data at source rather than have to curate things, but you can have a read of these if you want some clues. But just to give you an eye of what I think is good practice, this is a study, the Unite COVID study, published by ESICM. There's a large data curation process behind this, so we collected all this data, we published the data curation process, it's available on GitHub, so you can all go and look at it and decide whether you think we did the right thing or not, and you can criticise us if you think it was wrong, and we can rerun it with a new data curation pipeline if you think we've done something wrong. Here is the data curation pipeline. I won't read through all of it, but you can see down at line 23, we're importing the data, that's where it starts, it's a big file of data. So we take that data, and there we start messing around and fixing whether things are factors, whether things are integers, and so on. So this is kind of background stuff. Here I want to just draw your attention to line 900. It's quite a long document, this, right? 900, where it's saying if your FiO2 is less than 1, multiplied by 10. So we're fixing all those FiO2s that were put in not as percentages, but as fractions. Now I'm down to line 1,600, and it's a very long document. You'll see why I didn't give it. And we're fixing some free text problems. Free text is a disastrous thing, but there were some items that are collected as free text in terms of anticoagulation. And then we do all of this, and finally I get to line 1,704, where we finally would take the working copy of the data frame that has been now curated and pass it back to the user who can now do some statistics. I never changed the original data. All the decisions that are there and the team made are coded in this curation pipeline. You take the original data and you pass it through the pipeline. You never fiddle with the original data. Getting towards the end now, step 5, and this is tricky because it takes time and experience, is to develop a flexible tool bag. So I was asked recently to look at our community-acquired pneumonia patients in our institution and try and understand why some of them may stay longer than others and how we might sort of reduce this. So you can start with some simple tools and plot, length of stay, depending on whether antibiotic guidelines were adhered to or not, and let's essentially look at means and standard deviations and so on. But actually, the data is quite complex, and you're not really forcing it to give up its secrets if you just stick at that. So you might, for example, want to look at whether the outliers are different. So there you might want to look at the statistics of the skew and kurtosis of the distribution, not something we commonly do in research settings. You might want to try and understand whether or not there are some specific clusters of patients that are somehow different. And this is a dimensionality reduction of all the clinical factors of these patients into just 3 dimensions, and we can rotate these and try and look at whether. So this is a multidimensional similarity preserving dimensionality reduction process, which we borrow from machine learning. Okay, so and we see that in fact there aren't really clusters of particular similar behaviour. Okay. So then you might say, what about the system of care? What about where these patients go through the hospital? And then actually this becomes a network analysis problem. Now that's been well mapped out before, so you can start applying the network analysis tools. I overlay here patients who died and see in fact they're going all over the hospital. And you can start to, and we did that because we've used the network analysis before. These are tools that all exist. They've been applied in different disciplines and different domains, but you want them in your tool bag and you collect them over the years to actually apply to things. So finally, be green, recycle. And again, Leo spoke a little bit about this. This was a paper we published on cohort detection from, just one example, of cohort detection from Amsterdam UMCDB. So let's say that you want to go and look for something about septic patients in Amsterdam UMCDB. The first thing you've got to do is go through this really complex data set and find your septic patients. And you might do it one way, I might do it a different way because it's a programmatic exercise. So once you've done it one way and you think your way's really good and you've validated it and you think it has some merit and you've really characterized what you've done, publish it and make it publicly available. So you can take this code, it's on GitHub, you can apply it to the Amsterdam UMC database and you can get your septic patients out. That means that you don't have to waste your time doing what we already did. It means that you hopefully have some faith in what we've done because we published all the code and what we found and how we did it. And it also means if you don't like what we did, you can criticize us and you can publish your own code and tell us what we've done wrong. Okay? So it's really important to be open like this. I would say the one last thing, which is a little bit of a plug, which is get involved. This is a practical game. You won't learn how to do laboratory work by walking into a lab and being handed a pipette. And similarly with with data science, you can't expect on day one to be good. This comes with experience. I look back at some of my original code from many, many years ago, and it just makes me shudder. This isn't something that happens immediately. Lots of publicly available data sets out there. There'll be institutional data sets and problems that you want to address in your institution, of course. There are a number of datathons. Mimic has been running datathons for a long time. A little plug for the Europeans. We have been running a datathon actually for many years now. In recent years after COVID, we run them online over a longer period of time with people working in teams across the whole of the world over a period of a month, solving actually really quite important and useful real-world clinical problems. So that's an option of getting involved. So just in summary, number one, don't get in trouble, treat data with respect. Number two, think programmatically, definitely not in terms of spreadsheets. Number three is learn and respect the statistics. Everything has a statistical underpinning. Number four, take data curation and cleaning seriously. You will spend a lot of time doing it, but it is very, very important for data for reproducibility. Number four, then learn different tools for different jobs, and that comes with time and experience and working with other people. Share your code, preferably share code that you've proved works, and then finally get involved. Thank you.
Thanks very much. In the interest of time, we're going to move on. Just a reminder to the speakers that these talks are quite quick. They're 10-minute spots, so just to be mindful of that so we can encourage some audience participation. We're going to move on to Professor Bellomo from the University of Melbourne, who's going to be talking about natural language processing applied to delirium.
Thank you very much for your introduction. I'm going to focus about what we can do by looking at words. A little bit of philosophy. When you think about what delirium is, you might realize that it's actually a form of behavioral dysfunction with cognitive associated dysfunction. And it can be either naturally visible, because the patient is about to punch you, or it can be elicited. You ask the patient about some kind of question that a rational person will be able to respond to, and they don't give you a rational answer. It can be physical or it can be verbal, and we can only recognize it by observation. There is no gold standard. There is no diagnostic test for delirium. It's very different from hypokalemia or hypernatremia. And like all psychiatric diagnoses, it's a property of the patient, of course, but it's also a property of the observer. So what do observers do when faced with this state that the patient might be in? They can't do a blood test, they can't do an MRI or a CT scan. They can only interact with the patient either physically or verbally by looking or hearing or observing, and they can only report what they see in the form of words. There are no numbers around delirium. So the words that they use are nebulous, they're fuzzy, they're not clear. What does agitated actually mean? You might actually argue that I'm agitated, I'm just Italian. And so this uniquely offers us the opportunity to use words to understand this condition. And do words have face validity? Because if you're going to use words, do they mean anything to clinicians? Do clinicians have the ability to recognize certain words as more meaningful or more likely to define the people that they think are delirious than other words? So we gave them a mixture of words that have got some semblance with another that might describe people in a particular physiological or mental state. And you can see there are some words like agitated and agitation that are very different from apprehensive when you ask people whether they will connect one word or another with delirium. So there are words that have got greater face validity in terms of linking themselves to the concept of delirium. Then you've got all of that, and you can use natural language processing to go and look for these words and study what's going on in the intensive care by looking at cohorts of patients and trying to come up with an understanding of what information you can get. And that's what we've done. We published that in Intensive Care Medicine, and you can divide patients into what we call those with natural language processes diagnosed delirium or natural language behavioral disturbance, NLP, DXBD, or versus those that were identified as having possible delirium using CAM-ICU. And the first thing you want to ask yourself, well, does NLP diagnose a population where there is some face validity that these patients will be likely to be delirious? And then, you'll be looking for sickness, and age, and emergency, and illness severity, and that makes sense. So this approach diagnoses people by using words that have got some characteristics that would put them in the high likelihood of having delirium. And you can also see that using these words, you identify people that are more likely to be ventilated, have a worse gas exchange, a higher lactate. So it has some degree of clinical validity in terms of identifying such patients. Another way of saying, well, does it really identify people that we would think are delirious? Well, one way to look at it is whether they get antipsychotic medications. And the answer is yes, they do. And if you look at the different groups of patients that are CAM-ICU positive and NLP positive, and you look at those CAM-ICU negative and NLP positive, the NLP signal is the one that really matters. And so when you look at the outcomes, you might expect that these people you've just identified as being potentially delirious should also have worse outcomes, and indeed they do. So you're really trying to create a sense within yourself that all of the things that you've done with the NLP create a population that makes sense for a clinician's point of view. And so it does. It does in terms of patient selection, illness severity, characteristics, antipsychotic medications, and whether they live or die. And in particular, NLP positivity is the driver to antipsychotic use. CAM-ICU gets overwhelmed by the words that people use to describe what they see. Doctors, nurses talk to each other, and they react to whether somebody says the patient is agitated, the patient is bonkers, the patient is trying to punch somebody, I've had to restrain them. That's what people respond to, not to the patient I came ICU positive. Then we've taken this a little bit further to see if we can identify delirium subphenotypes. And of course, you can look at clinical notes and the words that people use to identify whether people have got hyperactive delirium, whether they've got hypoactive delirium, or whether they have a combination of both. Well, how do you separate hyperactive from hypoactive? Well, you use words that intuitively mean that somebody's hyperactive, like agitated, combative, restrained, uncooperative. You ask clinicians to separate these populations. They tell you what words they would use to identify one or the other. And then you can use word clouds to see what kind of words come up the most for patients that we think have got hyperactive delirium. And it's not a surprise that aggressive, agitated, agitation, restrained dominate. They're very different and very different word cloud for the patients that do not have hyperactive delirium but have got hypoactive delirium, and you can see the word cloud as it is. And agitated patients are different, not a surprise. So again, face validity. They're younger, less severely ill, they're more likely to be admitted after medical emergency team call, and they're more likely to come from the emergency department. They're more likely to be ventilated than non-agitated patients, and they've got all sorts of characteristics that you would think will be just what they would be expected to be. And in particular, you cannot be hypoactive, you cannot be hyperactive unless you've got the strength to punch a nurse. Most of the disturbed behavior can then be studied, the days when it happens can be identified, and then you can look at how people move from one state to another with alluvial plots, and you can see how delirium isn't a state that you either have or you don't have, and hyperactive delirium and hypoactive delirium are not a thing that you have and you take home with you, and it's a star on your chest that remains the same. You're moving. Some days you are hyperactive, some days you're hypoactive, some days you're both at the same time. And of course, as you would expect, it's the agitation that drives the diagnosis. It's the agitation that drives antipsychotic drug use, because the drugs that we have cannot cure or treat hypoactive delirium. If there were drugs that can make you think straight, I would like to be on one of them. The drugs that we have can only treat agitation, only treat psychomotor agitation. And you can see that it is the agitation that drives the use of antipsychotic medications. You're 7 times, compared to no disturbance, more likely to be treated with a drug that is antipsychotic. And of course, if you've got combined agitation and hypoactive, again, the same, the risk is there. And of course, combined behavior has got a particular different profile because there are biases inherent to it. There is opportunity bias, there is immortal time bias, because combined agitation requires time to occur for people to have both hyperactive and hypoactive delirium. So let me conclude by saying the natural language processing can be used to characterize behavioral disturbance in ICU patients. Such behavioral disturbance offers another model to understand abnormal cognitive and behavioral states in ICU patients. It identifies the importance of agitation in driving antipsychotic medication use and may therefore be practically a much more useful concept of delirium for the conduct of trials. Such agitation may be isolated or combined, and it's a part of a dynamic, fluctuating state of the patients. And using this information with NLP allows one to study the dynamic of this state shift by shift by shift, as reported by the nurses and the doctors. And it may be that this is a much more useful epidemiologic and clinical concept than delirium. And then let me conclude that when it comes to psychiatric conditions, and delirium is one of them, we're just modeling, because we've got no idea what the brain is doing, we've got no way of investigating it, and we create models in our own heads to interpret what we see. We only see the phenotype. We can't understand the brain behind it. And these are all models. And models are not right. They're not truthful. They're just a map. And they are just to be evaluated not on truthfulness, because the truthfulness is unknowable. They are to be evaluated on usefulness. Thank you very much.
Thanks, Rinaldo. So, although we're over, I have to ask one question. If we did the same exercise with temperature measurement and then asked or looked with NLP at whether the words cold, warm, hot of the skin was studied, you might ask yourself, say, well, I probably would judge how someone feels and then write the word cold differently from the nurse or the trainee. So all of this is stepped beyond the fact that apprehension or agitation to the nurse may be very different than to me. And that sort of gets to the internal validity of that word. So I'm wondering if you could comment on that.
Yeah, but the trickiness is you've got a thermometer, right? You can put a urinary catheter with a thermometer in the bladder, you can measure it. You can't put anything up the nose into the brain of the patient to measure delirium. There is nothing else. There is nothing else. All it is the observation. And so that's the only thing we have. And so you're locked into words.
I understand.
You're locked
Thank you.
into words. Yeah.
Thank you. So next, Ben Shickel from University of Florida is going to talk to us more about words on natural language processing in critical care.
Thank you so much. Yes, my name is Ben. I'm an assistant professor at the University of Florida, Department of Medicine. I am a computer scientist, actually, so maybe bringing a bit of a different perspective here. I'm going to take a broader view on NLP and critical care and touch a little bit more on the methodology and where we are now and where we're going in the future. Okay. So natural language processing. So I'm going to start with a very brief introduction of what NLP is, just so we can get a nice broad picture of this. So NLP is a subfield of AI that uses computational techniques to process data containing human language. So this is often represented as text, but sometimes also voice and speech can be considered part of that as well. So broadly speaking, NLP can be divided into two main categories: natural language understanding, which is about understanding sort of the meaning of words that's contained in text or in clinical notes in this case, and then natural language generation. So that's about obviously generating text either from structured data sources or from other textual inputs. So some of the classic NLP tasks you might think of are sentiment analysis, machine translation, entity extraction, text summarization, information retrieval, question answering, etc. So almost all of these have their analog in medicine and clinical notes. For example, here we see an image of relationship extraction where treatments, drugs, different other medical concepts can be extracted with NLP techniques, and they can be linked together to form a representation of a particular clinical note. So without getting too bogged down into the mechanistic details, I just wanted to take a moment to talk about how exactly a machine can process text, because I get this a lot in my job, working with clinicians who don't understand, because machines are ones and zeros, but text is text. Although I suppose it gets a little bit easier to understand with ChatGPT out and about now. But these are the four sort of popular methods for what's called vectorizing text. So it's turning text into numbers, essentially. First, we have this bag of words method, which is a purely statistical frequency-based approach where you count the occurrences of each word in a note, with the idea that frequently occurring words maybe are more representative of a particular note or a particular concept. So we can extend that notion with continuous bag of words and skipgram, which essentially use models, so that they'll use neural networks to predict certain things. So you can take these surrounding words from an intentionally masked out word there, represented by the question mark in the upper right, for SIBO, or continuous bag of words. You can use these surrounding words to predict a particular word. On the other hand, you can mask out these surrounding words and use a particular word to predict the surrounding word. So this could be a little bit in the weeds, but I think it's important to sort of at least visualize how this might work. So by training a model to predict what words should be filled into a gap there in a sentence. Across thousands and tens of thousands and millions, maybe even billions of examples, you might start to develop a model that has an understanding of what the words mean, right? So this is a big part of natural language understanding. Finally, the next token prediction is simply how modern models, such as large language models, learn. That's their training objective. That's how they learn. I get a little bit into that later. So very quickly, this is a list of some example applications of NLP in critical care. So I'm not going to read off the list, but you can see some popular ones, judging from the number of citations there. For example, in-hospital mortality prediction, sepsis prediction, etc. So lots of different prediction tasks. You have phenotyping tasks. You have information extraction tasks. This is half the list that I have here. So we have other things here. You can extract different occurrences from notes. You can do automated billing, automated documentation, lots of different instances of this in literature. And what I'm going to touch on as I get through this presentation is that there's some common themes here with the techniques that are used that are a little bit outdated, I would say. And some are updating methods to use the modern technology, but I think it represents a big opportunity moving forward to use some of the techniques that are being developed in industry and elsewhere outside of medicine. Really quickly, just to highlight a couple of studies in particular that all represent sort of a similar narrative here. In this study, they were looking at predicting ICU mortality with a cohort of 100,000 patients. A lot of these studies follow the same kind of pattern where they will develop a prediction model with machine learning to maybe predict this outcome that here is ICU mortality with structured data. So when I say structured data, I mean things from the EHR, like vital signs, lab tests, medications, etc. They'll do that first. Then they will add a feature set. For example, here they added temporal features, because in this particular study, they were looking at machine learning compared with ICU scoring systems like Apache and SAPS. In this study, they showed that adding the temporal features improved the predictive performance, but then adding the NLP features took it a step further. And so the NLP sort of unlocked the full potential of the model, resulting in an AURC of 0.92. This one here, they were looking at a model to predict who, among the patients admitted to the ED, who would eventually be sent to the neurosciences ICU. So this is a massive cohort of 400,000 admissions at Mount Sinai. They developed an NLP approach to essentially for ED to ICU triage, right? And again, we saw that adding the text features here sort of bumped up the performance to the next level, and here 0.93 AURC is pretty good for this particular task. Acute kidney injury, also a very important condition and syndrome in critical care. There are several studies here that look at NLP, what information can be gleaned from clinical notes in the ICU to help predict it early before it occurs, to predict recovery, predict staging and severity, and all of that. So these studies as well follow the same sort of narrative where the first person to come along developed a model with structured data, then someone else added text, showed it was a little better. I thought it was interesting here that somebody, a few years ago, they tried to develop a language model, which we'll hear about later in my talk and in the next talk, I believe, for just AKI patients, with the idea that the very specialized language model should be able to capture some very domain and disease-specific knowledge and context in the clinical notes, but it didn't work. And I think largely due to the small sample size, which is very, very critical for training some of these state-of-the-art models that you hear about in the news. So at present time, most of the applications of NLP in critical care have used small, manually annotated, task-specific data sets. They also predominantly use simple NLP approaches like bag of words, and statistical methods, or you might say machine learning, like logistic regression, linear regression, and things like that. So in recent years, we've of course heard a lot about LLMs, but before ChatGPT, there was this one called BERT. It was developed by Google. It's a different type of LLM, but it follows the same sort of concepts. It's a large model that you can extend for downstream applications. It's a pre-trained model. for this. So in this study here, they developed NYU Tron, which was a BERT-style LLM trained on this massive data set of 7 million notes at the NYU Health System. What was pretty cool here was that they found that they could actually predict patient outcomes using just the notes. So, up till now, I've covered studies that use the structured data plus the notes. Well, here, they showed that notes alone were enough to actually predict patient outcomes, including 30-day hospital readmission after ICU discharge, which, using their approach, was significantly better than what existed before that. So, don't need to remind you guys about ChatGPT. Of course, end of 2022 was released to the public. By January 23, it became the fastest consumer technology to reach 1 million users. A couple months later, it reached 100 million users, also the fastest in history. And it was a big driver of the current AI boom, is what the article on Wikipedia is called, that apparently we are currently living through. So I'm going to skip this slide in the interest of time, but I'm sure you are all aware of continuing efforts to deploy LLM technology into practice, I think largely for administrative purposes, whereas the research kind of focuses more on the predictive ability, predicting patient outcomes aspect of this. But in the real world, I think it's mostly about saving time through reducing friction of documentation. This is the important slide here. So I think in the past year, we've seen several kind of very popular landmark studies come out that show that these LLMs actually perform on par with medical experts, right? So we have things like answering questions better than physicians, showing more empathy, being more accurate on medical licensing exams and things like that, taking better consultations with patients, summarizing notes in a better way that is more satisfying to both patients and providers, et cetera. So I think moving forward, these LLMs are going to be a huge part of the landscape of NLP in critical care. But as till now, they haven't really permeated into critical care specific tasks, but they likely will in the coming maybe 12 months or so. This was a very deep dive into a specific task of medical question answering, which is a kind of prototypical task that demonstrates the knowledge that can be embedded into these large language models, which again are doing nothing more than predicting the next token. I'm going to skip this in the interest of time as well. So I think it's very important to note that healthcare applications of LLMs are still emerging, including those specific to critical care, and we're going to find out what those end up looking like very, very shortly. So in summary, there are several promising applications of NLP into critical care in domains like predicting patient outcomes, phenotyping syndromes based on behavior and other subtle indicators that are contained in notes, automated documentation, search, and more. So most of the existing NLP and critical care methods to date have relied on simple approaches in both NLP and machine learning and smaller data sets as well. So there's a real opportunity to apply more sophisticated approaches that are coming out constantly, right? Every week, every month, we hear about a dozen new techniques that apparently are state-of-the-art. So applying those to critical care tasks, I think, will be a huge future direction in this research area. So LLM-based tools have the potential to support clinicians in stressful, fast-paced environments, and I believe that the high volume of data associated with ICU encounters presents both an attractive modeling source, so the more data usually equals the better model, but also a target for their same application, so reducing that amount of documentation and distilling the information to only the critical concepts that will improve patient outcomes. So I think that is it. Thank you.
Thank you very much. We're gonna keep powering through, and so the next speaker is Azra Bihorac from University of Florida, Gainesville, who's going to be talking about a primer on large language models and prompt engineering.
Is it on? Oh, good afternoon, everyone. Thank you for attending this session. Unusual. Well, thank you, Ben. You gave me a great intro. I'm going to delve in more into large language models. So, first of all, let's start thinking why are they called large language models? What is large about them? Here you can see here that two key aspects of what's large about them. The first one, that they are trained on a large, massive text data, somewhere to petabyte size, pretty much scraped entire internet. That's how they are created. Second is the number of parameters that they have, their models, right? So you can see here that they all have the same architectural transformer. You heard from Ben. That was published back in 2017, and it'll be the paper called All You Need Is Attention, very true, by Google. And after that, you can see explosion in number of parameters, almost 15,000 more parameters between first modeler with 65 million parameters to 1 trillion parameters in GP3. Obviously, to train models of this size, you need an enormous amount of computational power. We are talking about thousands of GPU. Number of parameters go up, the number of millions of dollars you need goes up too. And really, only certain people or companies can do that today. Now, how can you use them? There are two ways you use them. You have a ChatGPT. You can simply pull your internet, a browser, and go on ChatGPT. Or you can use open source like Llama 2 from Meta. All you need to do is download one file. That's really so simple. File with all the parameters, weights, and then you have a maybe 500-line C code that you execute, and you actually have LLM on your desktop. Training them is hard. Having them is not. But what's really interesting about them, they are general purpose nature models. So what that means is they have a deep understanding of human language on a wide range of the domains. Now, how is that possible? So let's kind of dive into that. So how they compress data into parameters. So as I said, we are starting with a tera or petabytes of text data, mainly from the internet. And then you use neuronal network and transformer structure, as Ben showed, to find in each node, in each layer, the next most likely word. And then we compress each of that in the data. And that compression is really what is computationally very intense. And then we end up with a LLM-based model that is trained on a large, and it has a general purpose. Now, what was interesting, and for me it's the most fascinating about this, and reminds me of the science, is that as they start increasing number of parameters, once they pass 10 of billions, not a billion, but tens of billions, they notice something that calls scaling law, Chinchilla or KM scaling law. So what is scaling law? They notice once you pass 10 of billions of parameters, the model have emerging properties. It was able to have in-context learning, and it could follow instructions. That was not possible on a lower number of parameters, right? So that's what we are discovering. And that this law says it's number of parameters in the numbers of data and how much computational power you have. So that is the race we have. More parameters, more data, more computational power. Maybe we will scale to something else. I think that's what everyone is hoping for. But that is not enough. Once you pre-train the large language model, that is not what you have at ChatGPT. You need now to fine-tune them. Now, this is now where you need humans. And I would say, for me, I would write analogy with the parenting. The pre-trained large language module is like a child. And now what you're doing, you need to teach that child to be appropriate. So how do you do that? How do you fine-tune? So the fine-tune requires, as you can see here, once you pre-train GPT-3 on all of this data from web, you need to create another data set where you have examples of the dialogues of question and answer created by humans. And those question and answer then train this model, gear this model, steer them in appropriate answering appropriate way. So as you can see here, you can ask them like, what's the capital of Belgium? And not only they say it's a Brussels, but you provide answer, it's a beautiful city with a rich cultural language. So you basically steer GPT-3 to become polite, humans sound like chatbot, right? So humans are teaching them that. Again, it's almost like a parent. We have, you can refine them on separate, different tasks. ChatGPT is a general chatbot. This is one of our model, Gatortron, similar to NYU Tron. It's trained on the clinical notes to provide clinical question answering. Okay, so prompt engineering. Let's move on. What is prompt engineering? Okay, so how can you need to do prompt engineering, again, in order to use the LLMs. Similar to previous analogy with the child, you need to give them instructions. So you can shape the response of LLM based on your prompt. Crafting prompts is really an art of language use. So LLM effectiveness goes down when you have a complex tasks. So you need to break tasks in small steps, or you need to make tasks very specific in order to get a really good answer. Again, this is like creating an effective human compass for this model, gear them towards proper answer. Here is an example. Let's talk 4 major techniques, clear instructions. If you just ask, when is the next election? No answer. If you say, when is the next US presidential election? Then you get an answer. The providing context, you can see here, providing more context will gear you to a more specific answer. If you add persona, most of you now know, you need to say, think about you are a dog trainer, you are a doctor, you are a writer, think about this and so on. And then rules and limit. You can start being more specific. Instead of just saying, write me a poem, you can say, write me 200 words, poem that is in a style of Edgar Allan Poe, and you start giving more and more instructions, right? Again, very much when you steer someone who is very general and needs some directions. Again, very much like a parenting. Another technique is one-shot and few-shot prompts. You will hear those. One-shot means like you just give them a template. An example here is like you have a paragraph of you take your study and you say, here's my abstract, create me a social media post. Write it like this post, and you give an example. That's one shot. If you want now add more details in that example, like you see the little element, like graphic elements, you can get more eloquent posts. So more details you provide, more templates, a few short prompts, you're going to get better answers from LLM. Another one is a chain of thoughts prompting. What does that mean? Okay, this is very useful for any type of complex operation. Here you can have an example when you want them to do some simple arithmetic operation. You give them a problem and then you give an answer. And then you impose the next problem. You might not get a good answer, but if you break down the problem and you show them an example how you do simple arithmetics, actually they do better. Again, that's very much a very simple way. When you break the complex task by intermediary steps, you teach your student, and student then becomes your colleague. So this is finally a summary overview of LLM training process. Again, pre-training on large corpora of text, entree data using self-supervised training with a transformer architecture. You end up with a pre-trained large language model. You now fine-tuned with a very different type of data sets where you have a lot of paired, labeled question and answers, and then you have a prompt engineering where you can furthermore tune the model. Okay, LLM in medicine. Ben already pointed some of them. I'll just go very quickly over. You can see here I listed many of them for you. You can see that the number of parameters has increased over time, and you have a MedPal by Google with a 540 billion parameters, probably the largest medical model, and they have been used a wide range of tasks, ranging from the simple patient care task, mainly on a summarizing of text documents that we use in electronic health records. For education, probably very good use to personalize education, and some for the research. Probably in summarizing evidence-based, summarizing references, summarizing papers, using them for systematic review. They are getting better and better in this. And I think we can see really emergence of very good and powerful commercial tools very soon coming on for these purposes. Now, if only being a doctor is reading text notes and writing text notes or answering the questions on medical exam. Well, this is one of PubMed BERT. It's a pre-trained LLM for 6 biomedical NLP tasks used very much for medical extraction, medical information extraction. Maybe could be very good for the annotation of the clinical notes. That has been done lately quite a lot when we want to crowdsource data labeling with the different labels. Very good technique. Medical question answering, Ben went through that, and I can show you here that as you increase the number of parameters, here you can see more accurate answering of medical questions, and MedPalm has 86.5% accuracy on medical exam in the United States. This is another example, NYU Tron, where they used LLM-based system to integrate in real time in the clinical workflows to actually maybe train data not only on the text, but also on some other type of data, including medical outcomes, and then use that in operational prediction of medical outcomes. I think you can see that more and more. Here is our more latest work on our own algorithm, My Surgery Risk, that was initially developed using structured and time series data, but now we are embedding different type of data. We are using preoperative notes, embedding, and next will be images, and then you can see obviously more you put in the model, smarter it becomes, the accuracy goes up. So I think you can think about this almost like, what is embedding and what does it really mean? It's almost like putting the knowledge and data that we have in a format that this model can absorb as a knowledge and transfer it in some type of information. I think it really tokenization of not only text but other type of data is the next thing that you will see. There is a lot of open source, crowdsourced attempts to, as example, annotate everything and tokenize, Bible, everything that is open source, every religious text. People are doing that now. A bunch of students all over the world are tokenizing almost everything that exists. I think this is great. Maybe this is the way to preserve human knowledge. Big concern, as always, ethics, privacy, and safety. Many reasons for that. All of you know that, as I showed you, if more complex tasks they have, they're going to give you a very creative answer, beautifully polite answer, but it's going to be completely inaccurate. Now, that is a problem. You need to be aware of that. Everything that sounds good is not necessarily true. We know that. Another thing is that, this model has no real intelligence yet. So they are just replicate knowledge that is in the data they are trained on. So if any type of bias that data contains will be propagated in this model. This is something that we need to be aware of, and that's why they required a lot of reinforcement learning with human feedback to give them back some kind of humanity and some kind of limitations in terms of interpretation when they interact with you. So I think this is an important one. Regulation of LLM and generative AI in general is coming up in the United States. There is a lot of debate around this. I don't know what is behind in front of us, but I think it's important that as we restrain and regulate them smartly, we also do not damage their transformative potential, because it is very timely and critical that we use them to our benefit. That's all I have. Thank you.
Thank you, Azra. So we'll keep going next with Paul Elbers. He's from AMZ in Amsterdam with the next talk.
Yeah, excellent. Thank you, Chairman. And phenomenal to be here because it gives me the opportunity to convince you that you should share your data and probably also share my slides. I'll just start talking away because you probably know, as you are involved in intensive care medicine, is that intensive care can be considered a natural habitat for machine learning and artificial intelligence. But before I go into that, I should say that I have a conflict of interest to disclose, because our university is working with a company called PacMed, and I also have an academic bias as chair of the data science section. But back to AI in the ICU being a natural habitat for AI. You guys all know that, so because we have lots of data. We deal every day with high mortality, uncertainty on diagnosis and prognosis, and we make decisions every hour, every day, with big consequences. But let me put it to you this way: we have a big problem when it comes to implementing machine learning in our daily practice. So if you would ask me, is machine learning ready for takeoff in intensive care medicine? Well, I would say I currently doubt that, because as we have shown in this publication, 93% of models will stay in the phase of technology readiness level 3 or 4. So that means model development or model prototyping, whereas we would need to go to implementation, outcome evaluation, and model integration. And here are some of the barriers that are currently opposing that. And of course, they include a lack of understanding. So data scientists and doctors do not talk to each other enough. There is a lack of implementation because of legislation, security issues. But there is also a lack of data availability. And we'll talk about that a bit more. Because as you've seen in some of the previous talks, there's only so many intensive care databases freely available. So, and I've listed the most important ones here in green. So there's our Amsterdam UMCDB, obviously from Amsterdam, and there's HiRIT from Bern, Mimic from the US, and SICDB from Salzburg. Now, there are also some other initiatives in orange and red here, but they're either not readily available or miss a lot of data, and most importantly, some of the red ones are only available to the people that have built them. And I don't think that's a good idea, and I would like to encourage you to join the revolution and start sharing the data of your ICU patients that you created together with them tomorrow. So we've done a systematic review to compare the data sets that are already available for you to download. And because it is good to know there are very important differences between these databases. So just to give you an example, if you look at invasive ventilator usage or renal replacement therapy of vasopressors, so in other words, how sick are these patients, there's major differences with Amsterdam UMCDB probably having the sickest patients. So I'll focus a bit more on that now, and I'll show you our example on how we did this, so that you can start doing that tomorrow. So we published this in Critical Care Medicine, and just to give you an idea about the size of the data, so there's 1 billion data points in this database, and all of you can start downloading that right now. But of course, the main problem was that we needed to de-identify this data set to comply with privacy laws. And of course, you need to strike a balance there, right? Because you can, of course, understand if you do nothing about privacy protection, that the data will be very usable, but you would go against the law. Whereas if you would make it completely useless, if you de-identify it to such extent that you cannot do anything with it anymore. So luckily, the GDPR in Europe has actually defined data as anonymous if re-identification is not reasonably likely. So we're trying to find the sweet spot between identifiable, pseudonymized, strongly pseudonymized, and then at a certain point, the data becomes green and anonymized, and the GDPR does not apply anymore to the data. And to justify that the data has been reasonably de-identified in such a manner that it cannot be reasonably re-identified, we approach this mathematically by identifying the chance of re-identification, and that is composed out of 3 elements. So it is one element is the chance that you have access to the data, the intention you want to do something bad with it, and the technical chance you could re-identify that. And we have shown that in that paper. You can read about it by imagining 3 hypothetical plausible adversaries. So they include a friendly researcher, and he or she might inadvertently re-identify some acquaintance. Or you have the rogue researcher who is deliberately trying to re-identify someone using public information. And the worst one, at least in the Netherlands, should be the rogue insurance company who might, albeit illegally, try to re-identify someone using the company database. And so we basically de-identified all our data by using suppression and generalization in such a way that we would reduce the chance of re-identification mathematically to a very, very low level. And so we basically set the standards for anonymization in Europe, and has not been challenged yet, so it is de facto now the anonymization standard. Now, this is not something you can do very fast, because you need to do it rigorously, and it also implies you put contracts and governance mechanisms into place, because they reduce the chance of course, of access. So it's not freely accessible to just anyone, but only if an intensivist is co-signing. And we think that is a very good idea, because then you also start to promote that intensivists and data scientists are going to talk together. Also, just like Mimic, you need a proof of data integrity training, and all this has been reviewed by patient organizations, ethics persons, privacy committees, And of course, there's a controlled access protocol and a quality control cycle. So this is the result. It's a paper, but that is not the real result. So we also built models from those databases, and that has resulted in an application that you can actually now find at the bedside, predicting the risk of readmission. But it also led to more, because as COVID came, we started to think about how can we do this better and larger. So we started to share COVID data from Dutch hospitals, and this has led to the Dutch ICU data warehouse, in which also outside the COVID period, so now Dutch hospitals are trying to share their data among each other. And there's a European initiative, and I hope many of you joined that. It's called the Indicate Project, for which we have submitted an application for funding, and that is trying to collect data from all over Europe that can be accessed in a federated way. Now, this is all very nice, but I still would like to encourage you to make your data available to all, because the ICU Data Initiative and the Indicate Initiative are not as open as Amsterdam BioPCDB or Mimic or SICDB or HiRIT. And I think I would like to address the elephant in the room, because I think that clinicians and researchers still perceive their data as their property, and I don't think that is true. Sometimes they want to remain later in the field, maybe, and hospitals perceive data as a source of revenue, a claim to fame. Maybe they don't want people to uncover suboptimal practice. But I say to you that as intensivists, we have all learned from every single patient we have treated. And this is a virtue. So I don't think there's a thing as patient data ownership. I don't think that is a concept that can actually exist. And if it does exist, it shouldn't exist, because I think that healthcare solidarity is data solidarity. So can I please encourage you to start sharing your ICU patient data tomorrow? Then you would really help me, but you would also help each other in the community, and you will help your patients, and especially future patients. And with that, I thank you very much.
We have time for one question from the audience. If not, I have a very brief question, and that is, with the Dutch data warehouse that your jurisdiction has created, what's the governance like from each hospital? Like who sits on it, and who decides what data goes in and how it's used?
Yeah, for that initiative, there is a foundation called ICUdata.nl, and so there's basically participants from each hospital that govern the executive board, and there's also a scientific committee trying to make sure that sensible things go in and sensible things go out.
Great, thank you so much. We're going to move on to Edward Schenck from Cornell, who's going to talk to us about understanding machine learning methods.
Okay, so welcome everyone. I will, it's an absolute honor and privilege to be here, and I want to really take the opportunity to make this as simple as possible so that we're going to go back maybe a little bit higher level to just really be thinking about how machines actually think. My slides, I can see them, but they're not. There we go. All right. So my disclosures are as follows for my grant funding, but also I'm a clinician. I'm a clinician researcher, and I am definitely not a computer scientist. So let's try to look at some of the basic principles and visualize them so that we can understand all of the stuff that was really recently discussed a little bit more clear. So how do machines learn? That's the most basic principle that we can get to. It's basically they guess, and then they see how good their guess was. Trial and error is the only way that machines can learn. Okay, and what can they do? They can predict, otherwise known as supervised learning, and they can describe, also known as unsupervised learning. And so as we move on to prediction, conceptually, most of my talk is going to be these unitless X and Y axes here. So the Y-axis is your outcome of interest. The X-axis is your variable of interest. And as we think about this as a machine would, everyone is not a person. They are a point in a plane. with some value for your outcome and some value for your variable of interest. And if we're trying to look for relationships between these concepts, we can do it in several ways. Some of the most tried and true, I'm going to change our data around a little bit. Some of the most tried and true methods would be, is there a relationship between this variable x and this outcome y, which is a continuous variable? I forgot to mention that beforehand. Is there a relationship? So how would a computer go about finding the relationship? It would take guesses. It would draw a line there. That's not a very good guess. It could draw a line here. Not a very good guess. Getting better, though. And finally, it draws a line there. That's pretty good. How did they come up with this? This is linear regression in a nutshell. It's described by the equation of y equals mx plus b that you might remember from algebra class. But where did the m come from? Where did the b come from? The b is your bias. The m is the weight that you would assign to that variable x. Where did this come from? So with that first guess, that line, the relationship between that line and your variables is measured. And it's measured for each one of them. And that distance is the error function. And so the distance tells the computer how good the guess was. And they check that together in different formats. Some of it can be positive, some of it can be negative. And so you have to take the square of the distance. So it's a least squares methodology. And minimizing that least squares is how the line is fit. Okay, so for categorical variables, so a yes or a no outcome, you have some value x, which is a variable that you're interested in. It's associated clearly, unitless on the right side of the x-axis, so you're more likely to have a 1, versus on the left side of the x-axis, you're more likely to have a 0. This is modeled through this equation called the logit function, where instead of the equation for the line, you're taking the inverse of the equation for the line, and you're taking that to exponentiation of e. And so how does the machine estimate that? It takes different values for that equation, and then sees how good they are. The way that it's seeing how good they are, this is logistic regression in a nutshell, the way it sees how good they are is by this maximum likelihood estimation of how well that line describes as much of the data as possible. And if you move on to multidimensional data, you can see instead of just y-axis with one outcome of interest here, but you can have multiple predictors. So you can have depth in addition to your x-axis. You have a third axis here, z, and you can extend out differing weights for your regression, basically, and the machine can guess in multiple different ways. And so we are used to this. We are used to multi-variable logistic regression, linear regression, and it can be put together to come up with scoring systems. This is a recent example by the Spanish group for predicting prognosis in ARDS. And if we understand the relationships between variables, we can make really accurate predictions by putting these together. So the AUC was quite robust, and with scoring systems, you see stratification versus the outcome. And this is just simple logistic regression, which is in some ways a machine learning. What happens if your relationship is a little bit different, in that your outcome of interest is actually hidden amongst the variables where it's not simply a y? And so this is where more modern machine learning methods excel. So the way a neural network would work, instead of one variable x, you can have multiple variables feeding into multiple models where the weights, so the m values for that, that coefficient that goes into the generation of the line, gets to be different for each one of these three models. So your variables are contributing data to multiple models that converge on an output. And so you can picture this as a neural network would create something where you have multiple different lines that are partitioning a point, an area of interest. And so basically this allows you to look at nonlinear relationships or more complex relationships that you wouldn't normally be able to look at through traditional logistic regression. It still uses loss functions, and you can actually move up a step with this and combine data together for hidden layers where the relationships can be even more nonlinear, more complex, and you have things that can be tuned such as hyperparameters. Example of this is using neural networks to define the volume of bleeding inside of intracranial hemorrhage. All right. To summarize, prediction or supervised machine learning is through error minimization, and it excels at defining complex nonlinear relationships that we don't understand normally. And then the prediction is also things that, like things like random forest and X-gradient boosting, which is beyond the scope of this talk. So description, we have our data set again. We have soft clustering methods, or Gaussian mixed models. This is the fancy name for latent class analysis or latent profile analysis. And basically what a Gaussian mixed model is you're taking a Gaussian, which is a normal distribution in three-dimensional space. We're looking at it from the top here. So the center is this little oval. The center is this little oval, and the probability of membership in this model gets less as you extend to the edges. And the machine is just going to guess differing distributions on your data, and it's going to stop guessing when that distribution defines most of the data. And you can see, but it's still, even though it's encompassing a lot of the data, it's still not perfect. So then you could try two models where you're guessing different distributions, and the two Gaussians are representing the data better than the one, so 2 is what was picked, and it's called a soft model because it's probabilistic, and the two models there share overlap with probability of the two patients in the center. That's kind of the science behind a lot of the latent profile analysis or latent class analysis that we've seen in critical care. This is the original Kalfi et al. From the ARDS papers back in 2014. Then hard clustering mechanisms are not probabilistic. They do sharp demarcation in terms of how they define different groups. So k-means, how is this actually done? The machine takes a guess at a center of a group and then measures the distance between all of the points in that center guess, and then guesses again and measures the distance and tries to minimize that distance with every point within the group, and keeps going until it is in the absolute center. And then it does the same thing repeated with multiple groups instead of just one, and the error mechanism is a little bit different than in the latent profile analysis, but it's still using an error mechanism in terms of how well the two groups define the data. And that's k-means clustering, which was behind Chris's work with the Seneca trial back for sepsis descriptions. So in total, machine learning is able to perform predictive and descriptive tasks exceedingly well. It excels in situations with lots of variables where their relationships to each other are unknown. It can help us define nonlinear relationships, more data the better. External validity is critical to effective patient-centered goals. You have to ask yourself when you're interpreting models is how would this prediction help? Do the descriptions reveal something useful? And lastly, can the descriptions be predicted? All right, thanks very much.
So thanks, Ed, for making a tricky topic very accessible. So appreciate that. We're going to go ahead and finish with our final speaker of the day, which will land us on time, and that's Matthieu Komorowski.
All right. You guys okay? It's pretty relentless, not that pace of talks. Well, thanks for still being here. So we're going to talk about the byte to bedside gap. Here are my conflicts of interest. What gap? Well, Paul described that gap really well, and here's another paper that just says exactly the same thing. And this is a survey, a review of AI applications in the ICU, nearly 500 papers, and what you see is everything is at the level of model prototyping, early model development, very, very little prospective testing, deployment in a clinical setting, randomized trials. Some of the ideas I'm going to share were discussed over the last few days during the roundtable. So some credit goes to some of my colleagues there. But if we take a step back, the process of developing and deploying those tools into clinical practice, it's a 3-step process, and you need to start by having data available, obviously, building your model, and then deploying it. Having access to data is getting much easier. We've heard about all of this. Obviously, I need to highlight physionet.org, but the one thing that I think no one has talked about is the open access imaging databases that are becoming available. Here's CheckSpert here. There's also Mimic Checks X-ray and a large number of other papers, other data sets available. So the data is available to some extent if you want to get started at least. Developing the machine learning model is by far the simplest step in this process. I'm not even going to talk about it. If you want to build a neural network in Python, it's 2 lines of code. It's very, very simple once you have a clean database. I'm simplifying, obviously, but deploying those models is where the challenges continue, and I think that's where some of the most significant challenges are. If we want to phrase it in a different way, machine learning is important. Obviously, it's the core of the technology, but it's only a tiny piece of a very complicated puzzle if you want to impact patients at scale. And there's so many other things that you need to consider. And I'm just going to list them and give you a few examples of the ones that I think are the most painful. So technical challenges to start with: data interoperability, lack of data quality. Those models ideally must be generalizable, meaning if you train a model in the US, you want to make sure that it works in Belgium, or you're going to have to retrain your model locally. Interpretability / explainability, not strictly speaking, not a very strict requirement, but for many users, very, very important. Okay, one example here, 16. 16 is the average number of EHR solutions per hospital in the US in this particular survey. They surveyed 4,000 hospitals, so it's pretty exhaustive. So meaning all these systems are not interoperable. They don't talk to each other. If you want to collect data on mortality and lab tests, you usually use two different EHR systems. If you want to give you one example from my own research, we built an AI at Imperial, and it took us about 1 year to connect the same AI to a hospital at UCL where Mervyn Singer works, because it was a different IT system. It's very, very significant. It's such a significant problem that there's hundreds of companies popping up like mushrooms trying to address this issue of and working on health data infrastructure and interoperability. Next, human factors. There's a lot of literature on, for example, here, the technology acceptance model. So formal ways of improving the acceptance and the use of a new technology. What some of these models ignore, in my opinion, is that sometimes there's a gap between the intended effect and the measured effect. And here is an example that's very striking, in my opinion. This is an AKI alert randomized trial. There's no AI involved, right? It's literally just looking at the creatinine levels, and if you cross a threshold, then there's an alert that pops up in your EHR system. Okay, they randomized 6,000 patients, multi-center study, beautiful paper, and they looked at progression of AKI, dialysis, and mortality. Okay, what they found is no difference anywhere, except in non-teaching hospitals, the mortality nearly doubled. So by deploying a digital technology that you think looks really, in principle is going to be very, very helpful, you observe a very critical side effect of increased mortality. Obviously, they discussed this at length. There's no clear explanation from the study as to why this happened. But for me, that's a really big flag. We have to be careful. We have to be we have to progress in a stepwise fashion and put patient safety first. Speaking of prospective testing, this is Paul was the senior author on this one, a systematic review of machine learning for sepsis prediction. This is 4 years ago. What they found back then was 28 papers. Out of those, there were 3 prospective trials and only 1 randomized trial with 142 patients. To my knowledge, this is still the case. So machine learning is a huge topic. Sepsis prediction is a huge topic in machine learning, and even to this day, to my knowledge, there's only 1 randomized trial with a very small sample size. So it is a complicated thing to do. Next, items around information governance, trust of patients, inclusion, algorithmic fairness, involvement of members of the public in research. This is all critical. Here's another number for you, 60%. So 60%, that's the percentage of Americans who say they would feel uncomfortable with a provider relying on AI in their care. This is a recent survey, December 22, 11,000 people responding and coming up with this rate. So again, that means careful. We need to progress. with full transparency, full accountability about what we're doing, how we're using people's data, and obviously keep everyone in the loop. Algorithmic fairness is in everyone's mouth, and it's a good thing. What remains to be done, in my opinion, is to define what it means, algorithmic fairness, and to also operationalize it. And this is an interesting paper. They looked at, in publicly available data sets, how could we assess algorithmic fairness? What data is available in those data sets to actually start to address this question? Does my algorithm perform well in ethnic minorities, for example? Well, you see that table is very scarce. There's a lot of missingness there. So operationalizing the assessment of algorithmic fairness is going to be a tricky thing to do. And last but not least, the exit strategy, right? Once you have your model and it's validated and it's fair and people like it, you have a good interface, then what do you do with this? Well, then at some point you need to develop a medical device or hand over to someone who will for you. And that means dealing with also protecting IP, dealing with regulators, doing health economics analysis, things that academics, myself included, have no experience in. We can look at the end of the pipeline, the devices that made it to FDA approval. So the latest list has nearly 700 AI-enabled devices approved by the FDA. You see that the bulk of them is in radiology, and the top dogs there are big companies, right? Really big companies: GE, Siemens, Philips. You see, and it's unclear. It's TBD, in my opinion. How do you navigate this as an academic? I want to finish with a picture of the team I'm working with in London on this question. You see how multidisciplinary it is, because I think that's the only way to even make a start in addressing some of these challenges. So obviously we have clinicians. Tony Gordon is my boss. Then we have machine learning people. We have software developers, very different job. We work very closely with the NHS informatics, human factors, health economics, PPI, medical device development, clinical trial managers. And there's even more people involved. So to conclude, yes, there is a gap. Yes, there is a big gap, but somehow I believe it's expected that such a gap would exist, given how complex that process is. And maybe a more optimistic way to look at it is to compare the process of developing drugs by pharmaceutical companies to this idea of this concept of developing AI-enabled tools in healthcare. And but what we've been doing is a lot of algorithm discovery, preclinical testing, and slowly there's a few products that are making it down the pipeline towards becoming an approved medical device. Thank you.
Perhaps to give some time to the next session for people to switch over, we'll wrap it up there, but really like to thank my co-moderator, Dr. Chris Seymour, as well as all the speakers for just a really wonderful set of talks, and to the audience, thank you so much for attending as well. Thank you.